but it's sort of like there to exploit. So this is just sort of a kind of example experiment from the paper that we had done in June. So this is just, your sort of canonical MNIST task. You have a bunch of handwritten digits and you want to classify them. The spin here is that, okay, well, now let's talk about robustness. So we sort of add like a little bit of noise, a little bit of Gaussian noise to each of the values in our data set. In this case, it's just 10% noise, so just like a little bit of noise. The density in N and the sparse net, which roughly has about 40% of its weights on, about 10% of the activations on, does like fairly well. As we go up, we increase to 30% noise. The density in N doesn't really do as well. Sparsity in N is sort of like kind of kicking in there still. Obviously, at 50% noise, things aren't really going that well, but the sparse net is doing like just sort of comparatively much better. So that's nice. Okay, so that's sort of like the kind of stuff that we want to do with sparsity, the stuff that we worked on with activations. We're also now working on training with sparse weights. So I won't necessarily talk about those particular things because it's sort of like in progress and sort of being iterated on. But this is a Ray talk, and so let's talk about Ray as far as we use it. So there's kind of three things that I would say really give us a sort of benefit to Ray. I mean, overall, it helps streamline our experiments, but three things in kind of particular. So two of them are represented up here. If we sort of like look at the top, one of the things that we kind of got excited about is, okay, well, this is a nice, neat way to sort of like encapsulate our experiments and sort of like help us make things like more modular. So we wanted to have our library, which is newpick.research. We have these frameworks, and we wanted to sort of make our data sets modular, our models modular, our networks modular, and sort of just have it very simple where we have this Ray trainable and we have this setup. It says, okay, from the config, define our data set, define our network, define our model, and then let Ray, take the wheel from there. And so the second thing that Ray obviously helps with is that, they have the nice like Ray tune library and a lot of great functionality for that. So, hyperparameter search, of course, you can do, random search, you can do, grid search, you can do random search. And then there are also some sort of like, fairly easy ways to sort of get more sophisticated search algorithms working in there. One of the people on our team has recently been using Axe Search, which is out of like Facebook. So this is just like one example. Obviously, there's like tons of different things that you can use, but it's been fairly helpful for us. So, we want to try to test out different sparsity levels or, whatever have you. Ray sort of like helps kind of sort of streamline that. So the other thing, which is a little bit more recent, now we wanted to train like bigger models. Like, okay, fine, we have, Spark activations working on MNIST. That's great. Everyone's doing MNIST. What if we can sort of get on bigger data sets and bigger models? And then, of course, you sort of like run into the situation. Okay, well, now we need to run on a bunch of GPUs and coordinate that. So PyTorch has some nice libraries to help you, sort of distribute your model throughout multiple GPUs. And so, just kind of like conceptually what that looks like. You have some batch size, say it's like 64. You split it up, 8888. And then, so this is like on the PyTorch end, of course. But the really neat thing about Ray is that in terms of like setting up these GPUs, instead of having to sort of like manually set them up and sort of like tell PyTorch I'm using this GPU, I'm using this GPU, so on and so on, or even having to instantiate those on AWS, there's this auto scaling feature of Ray, which sort of kind of on the fly just creates as many like worker nodes as you need. So that's been quite handy. Okay, so that's pretty much all I have. It's sort of kind of a bit at the high level of what we've been working on, things that we care about. We care about sparsity and just a high level of why we care about Ray. Thank you, Ray. But that's it. Thank you. Of course, any questions? Okay.
Questions? Mike, can you describe about the node architecture? Are you using Kubernetes? What is your cluster looking like? To repeat the question.
Okay, yeah, he asked what does the node structure look like, and am I using Kubernetes? So we're using Ray. I don't necessarily know exactly what it means to say like what does the node structure look like.
I mean, what is it running on?
What is it running on? Oh, it would be on AWS. Does that answer the question? Yeah. So I don't know if like Ray Autoscaler also works with Kubernetes. Does it?
It works with Kubernetes.
It does work with Kubernetes. Thank you. Yeah, we in particular just use it for AWS, and that seems to suit our needs like quite well. Yeah. Yeah.
Could your robustness to noise be applied to like self-driving cars? Could there be a good application of that?
Yeah, that's a good question. I mean, I think oh yeah, sorry, yeah. Okay, so he asked, can the robustness to noise be applied to self-driving cars? So the first thing that comes to mind is the issue that they have with adversarial examples and sort of things in that realm. And actually, I was thinking about on the Caltrain over here, I was like, wow, I'm surprised we haven't tried to do some research with this into adversarial examples. But it seems like it would be, I mean, because that's kind of like what those things are about. So I would suspect so. And hopefully we'd get around to at least trying something with it, but yeah. Was there a question?
How much speed up can Ray give?
How much what, sorry?
Speed up.
How much speed up can Ray give us? I would guess it's more about a speed up in terms of time, right? Personally, I'm not fully familiar with all the different like engineering like solutions that are out there. But I would say that it has been decently straightforward, but I don't know how to like quantify that sort of differential and time improvement. Yeah. Yeah.
In your sparse network, are you using like 32-bit scrolls for each of the weights, or do you also try? I mean, I'm not an expert in your computing, but I always heard that in the argument that
oh yeah, you go by you
smaller resolution on the weights.
Yeah, that's a good point. Okay, yeah. So he was asking with the weights in the sparse network, do you use like float 32, or do you try to use like a smaller size? And then he also mentioned that neomorphic commuting, they sort of maybe use smaller and smaller data sizes. Yeah, so actually the thing, if you look at some of our past work, it was all about actually binary networks. Everything that we did was just like binary networks. As to sort of kind of get our toes wet into machine learning, it was just like working with float 32. But we actually do have a lot of interest in terms of binarizing our networks, or or at least doing some form of quantization, but not just yet. Okay.
All right.
All right. Well, thank you all.
Hi, I'm from Microsoft. Oh, can you hear me better? Okay. Okay. Yeah, my talk is gonna be short. I'm gonna try to, talk a little bit about what we do, in my team that I work on, and how we leverage on Ray and Arlib. So this is a quick summary of something that we believe on. Is about that reinforcement learning is going to be well established. We think that is going to happen, and it's going to be really close to distributed computing. So some time ago, we have to decide between moving away from doing everything by our own means towards using something that is out there, right? So we put the bet on Ray and Arlib. So this is the agenda. I'm going to talk briefly about what we do, how we do it, and talk about Ray and Arlib. So what we do. So our value proposition is machine teaching. It's just a way to, take knowledge from people and put it into machine learning algorithms. So it's intended for people that do not work in machine learning or computer science. It's a complete solution for building, training, and deploying brains. We use that name to refer to the models that we produce. And yeah, we use mainly deep reinforcement learning. So this is a quick description of our toolchain. So yeah, and the experience that we offer to our early adopters is about, we are providing a kind of language. Yeah, it's a language to, write down this knowledge that you have and put it into the brain, right? So we provide tools for simulations, we provide tools to actually train, and also to deploy, okay? So this is how it looks like to our clients. And yeah, we have good examples in that website. I can provide the slides after. These are really, really nice examples of very successful projects that we have. The most interesting one for me was this one. I think it was with Shell. I don't remember, but it's really, really nice. I don't want to go too much in detail here because I want to talk about Ray. So yeah, So this is a very, high-level description of our architecture. So as you see, we use Ray, to support our distributed computing, or at least part of it. There are way far more stuff there, but Ray's in the middle of our platform, our services. And on top of that, or inside our services, we have the machine teaching engine, which is this artificial intelligence engine. We have this compiler for the language that we have. And yeah, RLib is a big part of our engine, our AI engine. So yeah, for us, Ray and RLib are critical. So and actually it has been quite important to move faster, because before we were doing everything. So everything means distributed computing, code, and also machine learning algorithms ourselves. So now we are pretty much getting away from that thanks to Ray and RLib. So, and this shows us what we want from Ray and RLib. So let me talk a little bit about our history. So as I said, at the beginning, we read everything. So after we realized that if we want to move fast and achieve what we see, the value proposition that we want, we need to use open source things. So at the moment, we evaluate different options, like the one from Facebook that I think was called Horizon and now is Re-Agent or something like that. TensorFlow agents as well, and yeah, another stuff. And we select the whole team select Ray and RLib. So today we are almost full on top of that. We are still catching up with the latest versions because Ray is moving faster than what we can do, which is good. And yeah, so today we are trying to get involved in the community. As of now, we are not contributors. So in the midterm, we see ourselves as contributors there. Yeah, in the future, we want to be fully focused on our machine teaching, value proposition, and rely in RLib and Ray for, this very core internal thing. So yeah, that's pretty much. I don't know if somebody have any question. For example, this question about Kubernetes. We use Kubernetes. We are not using the autoscaler, for example, but we do use Ray on Kubernetes successfully. Yeah.
Questions? Answers?
Maybe a quick one. Can you elaborate on how your team has decided to, for example, favor RLib over Horizon from Facebook? It's a question that is coming to us also quite often.
Okay. Yeah. The question is how we decide to choose Ray and RLib instead of the other options. Yeah. There are a lot of factors to consider. So I think the first one is Ray itself. It's quite. So if you work in machine learning, you want to keep close to Python, right? But because it's distributed computing, you need performance. You need some sort of high level things in the computing size. So turns out that Ray was the only one that was actually working very close to a deep reinforcement learning thing, but with a lot of focus on distributed computing. So that was, very key at the beginning. And the second main reason was RLib was incorporating algorithms at good pace, and the implementation, looks good for us. We already have the implementation, so it was not key at the beginning, but we realized that the implementations are good. We performed some tests, so we realized, what, we can take this code, we can use it, and we can start, investing more time in our stuff instead of doing the thing that somebody else already trying to solve. So yeah, I would say those two things: computing of Ray and the algorithms that you are taking from RLib. Yep.
Anybody else? All right, thank you so much.
Yes, sir.
All right, let's see. All right, can you hear me? Yes. All right. Hi, I'm Simon. I'm a software engineer at Anyscale, and today I'm going to tell you about RayServe, which is a new scalable machine learning serving system we're building on top of Ray. So just to put RayServe in the whole ecosystem you have seen today, we're a library sitting directly on top of Ray, similar to RLib and RayTune. And from our lack of logo, you can see we're really new. We don't even have a logo. And okay, so just to keep everybody on the same page, what is machine learning model serving? If you think about if you are pushing machine learning to production today, there's 3 steps. One, there's model development. This is where you train your model, collect your data, featureize your data. And there's, of course, training, and this involves a lot of distributed, iterative process, and this is also what Ray can be really good at. And last step, there's inference. This involves after you train a model, you need to wrap your model in a prediction service, and for it to interact with the end user application, so the end user can directly query your model and get a result back. So we're really thinking about, when we're talking about serving, we're really thinking about how to serve predictions for large-scale interactive applications. So there are 2 common approaches I'm going to discuss today about how, in general, this kind of machine learning model serving problem is approached today. So there is one approach I call embed model evaluation inside the web server, and an alternative approach that is to offload prediction to an external service. So let's discuss the first one. And for the embedding model evaluation in the server, right here you can see typically we can have a HTTP server. Right here I'm using Flask, which is a very popular and simplistic Python web framework. And we can define several like API endpoint, like health, DB query, or even gathering images using API endpoints. And then if we're going to add a new machine learning service endpoint, we can just say, for example, right here, we'll add /API/image predict, and then inside the handler of this API endpoint, we can directly call, for example, TensorFlow for model evaluation. So this approach is definitely simple. And in fact, this is by far the most popular approach if you search how, if you do some research about how like people serve model today on GitHub. And of course, this also enables you to have end-to-end control over how the model is exactly served, because you can define your service endpoint as well as define how the model is evaluated. However, this has some downside. One downside includes you can only process one query at a time, and model is reloaded once per the sort of server lifetime, and typically in this kind of framework, it's loaded as a global variable. And additionally, this approach has no isolation. What do I mean by that? Is that your slash sort of DB query API endpoint lives in the same process as your model serving endpoint. If your model server crashes, all the other API endpoint also crashes. And lastly, there's no fine-grained replication. If you are serving multiple models, you have to put them all in the same place. If you want to increase the number of replica, you have to replicate the server itself as well. And I will also focus on this one biggest issue, I would say, to this web server approach. That is process pool-based deployment method. Typically, in this kind of deployment, you'll have some initial process forking off the web server, and there are multiple replica of these worker processes. And then requests are just load balanced among these worker processes. This definitely works if you have a database query, if your API is just serving some static files. However, this kind of breaks when you're serving machine learning models. For example, right here we have 3 TensorFlow models in one process. And because the processes are replicated and forked to many different replicas, we soon end up with many TensorFlow models in our memory. And of course, this will soon lead to memory issue and also resource contention issue. And another downside of this kind of web server-based approach is that it is so simple, it doesn't offer you the ability to orchestrate complex pipelines. So right here, if we see the circle as a single model, what typically happens in production is that the model is composed in some sort of pipeline. So right here, you can see a simple linear pipeline. But of course, there could be different patterns. Right here include A/B testing. We can have the same model trained on different data, or the same model trained in different method, or just using different hyperparameter. I want to test how good it is. So we'll split the traffic between different models. And there's also the reverse of this kind of approach, that is to use ensemble to sort of vote and select among different output from different model, and finally, sort of, for example, taking an average of the output and then send it out for the user. And there's also approach like Cascade, where when an upstream model can output a high confidence, when it's outputting a high confidence result, you'll go directly to the user. However, if the model is not confident about the current result, we'll directly send the input to more higher quality, slower models. So in summary, this kind of web server approach is simple, but whenever you need to go beyond just one single model or go beyond just one single replica, you'll soon break. This is why people are starting to go to the second approach, that is to offload prediction to an external service. So we can have our same API definition right here, and then the model evaluation is then moved to right here, represented in a cloud, that is the external service. And this approach, typically, you can see example include TensorFlow serving, Onyx runtime, Seldom, TensorRT from NVIDIA, and of course, AWS has this service called SageMaker. For this approach, I want to discuss exactly how it works. So if you can imagine how typically when a request for machine learning model service come in, it comes in via HTTP, and then you do some API validation, and then the data is going to business logic. And then you need to do input transformation, wrangling, and then you put it through, say, PyTorch or TensorFlow, hit the session.run, or do the model.evaluation. And then finally get the result back, wrangle it a bit more, and then process another layer of business logic, and finally return the API output. This is all good when the entire flow of process is running inside a single web server. However, when there is an external service, first, the inference stage is moved to the external service. And additionally, the input-output transformation steps are kind of spanned between the two services. And what I call these external services are mostly tensor in, tensor out system. For example, if you have an image classification model, then when you take the bytes from the API, for example, parse the JSON, JPEG decode it, and then we want to do some maybe color correction, normalization, image preprocessing, crop it, and then finally convert it into a three-dimensional RGB vector. And then we can send that as a numeric array to the external service. And after the model has done evaluation, what we get back is another array of numbers. But however, we cannot directly return that to the API endpoint. That means we have to do another layer of output transformation, business logic, and transform to some, for example, English labels people can understand. So this is what so this approach brings complexity. And well, but you may imagine like the whole reason of this approach is to separate model evaluation out of the whole web services. But this kind of separation means you have to manage these two services separately and deal with them separately. And because this model evaluation logic is split from business logic, these models are harder to configure, harder to learn, because there are new custom systems, and also, of course, harder to debug. Just imagine you have your data scientist to learn the RPC system, to write RPC code, to do all the validation, and think about learn how to directly talk to and configure SageMaker or Onyx runtime. It's very hard. So when we're building Reserve, we have several goals in mind. We definitely want to stress for simplicity. It should be as simple as a Ray API is to get it up and running. And then additionally, we are aiming for end-to-end control as a data scientist or as engineer to control the whole workflow from API endpoint to model evaluation and back to the API endpoint. Additionally, with Ray, we want to enable complex machine learning pipeline as well as scalable pipeline to span across many, many machines. And of course, Ray, one of the biggest advantages of Ray is to give you this programmability to program over the whole cluster and manage all the actors inside the system. And of course, you need to observe the whole system. So this is what we offer today as RayServe API. You can decorate the API endpoint with served routes, just like you did in Flask. The model is loaded as an instance variable instead of a global variable. It is bounded to this process, bounded to this actor, if you are familiar with Ray actor model. That means if it crashes, it won't impact the whole system. And when you are processing queries, what you take in is a Flask request. This is what people are most familiar with, and especially for data scientists, this is their first sort of web server